So, any questions? Oh, this wasn't it, was it? No, that was the other thing. It was kinematics. Wait. I'm having deja vu here. I feel like... It was page 12? Yeah. Oh, okay, so it was that. Did anybody have any questions about that? I was just seeing that fishing reel there again, thinking I've already talked about this. And that 220 again. But Mr. Pennington was just on a 220 kick at that point, apparently. No questions? You're all good? I hope that means it was just easy. Hope so. All right, so the new thing is, for today, rotational kinetic energy. So, get my pencil. It kind of looks like a set of problems rather than notes. Starting with linear or tangential kinetic energy, or if you look at the copy of the notes I have, I've crossed this out. And another way of saying this is translational. I believe I heard that people are doing different kinds of transformations in math, or at least you've done those. There are translations, there are rotations, there are reflections. A translation just means if I had a smiley face and I translated it, I could move it to here, or I could move it down here, like that, versus a rotation where, you know, this might rotate around this axis and then it would look like that. So translational just means in a straight line. Translational. And usually when I talk about linear kinetic energy now, I call it KE with a little T under it. So this is the kind of kinetic energy that we've been working with up until now. It's 1/2 mv squared. So, but now we're going to have a new one. We're going to have KER, which is rotational kinetic energy. Derive a formula for rotational kinetic energy of a single mass m with the velocity v revolving around an axis with the radius r. So that would just look like this is the axis that something's rotating around. This is the mass m. This is the radius. So this thing is just going around in circles, basically. So to do that, I'm going to bring in I, which we went over yesterday. So the moment of inertia for something like this is just mr squared. That's the moment of inertia of a one point of mass moving around something at a distance, at a radius of r, with the velocity v. Well, I guess we don't really have v in here right now, but it's got a mass of m. And from this, if I solve this for m, if I want to isolate m, I can just divide both sides by r squared, so I get m equals I over r squared. And there's one other thing I want to roll into this, which is the relationship of linear velocity to angular velocity. So if you want to convert radians per second to meters per second, the conversion is radians per second times the number of meters per radian equals velocity. So now, sort of putting all of this together, KE, which I'm starting with right here, I'm going to substitute this in for m because m is equal to that. So I get 1/2 times I over r squared. And instead of v squared, I'm going to use this. I want to use omega. So really what I'm going to substitute in is omega equals v over r. So 1/2 mv squared becomes 1/2 times I over r squared, which is equivalent to m, times v squared, which is, what did I do? No, I guess I don't really need that yet. I'm going to need this later on today. I just want to do v squared. So this is omega times r squared, because it was v squared. So simplifying all this, and I'm going to call this rotational kinetic energy. Rotational kinetic energy equals 1/2 times omega, or sorry, it's not just I omega, it's I omega squared. So the I doesn't get canceled out. The r squared in the denominator, there's an r squared in the numerator, so the r's go away and we're just left with omega squared. So this is a lot like that, really. It's the moment of inertia is the rotational equivalent of mass, and omega is the rotational equivalent of linear velocity. So it's not hard to remember. And how you get from this to that is not that important to remember either, but I just wanted to show you. It's nothing really magical. It's kind of cool. All right, and the math we're going to do here is kind of cool too. This is a place, solving these kinds of problems, if you run into something that says something like a cylinder rolls down an incline, your antenna should straighten out and alert you to the fact that you should probably do as much as you can algebraically before substituting in numbers. This is a good time to not put in any numbers until the very end. So I want to calculate the final speed of a solid cylinder that rolls down a 2-meter high incline. Starts from rest, has this mass, has this radius. Let me just really quickly draw this. I don't want to use space in my paper, but it would look like this. Here's the cylinder, starts from rest, and it's going to roll down here, and we want to get the velocity here. And if you think back to conservation of energy, it's going to have one kind of energy here and another kind there. What kind does it have at the top? Potential energy. So the potential energy it has here is going to be equal to mgh. Oh, mgh, just one h. And the energy that it has here, it's going to be all kinetic. But it's not just going to be 1/2 mv squared anymore. It's going to be 1/2 mv squared plus 1/2 I omega squared, because it's going to both be moving translationally, and it's also going to have some energy that's bound up in the rotation. So I'm not going to write out the whole conservation of energy formula. I'm just going to set it up as mgh equals these two kinds of kinetic energy. So mgh equals 1/2 mv squared plus 1/2 I omega squared. And I'm gonna try to conserve as much space as I can, because I didn't give you a whole lot of space here. So the first thing I'm gonna do is work on this. I've got too many different variables. I've got angular velocity here, and I've got linear velocity there, and it's asking me for final speed. So really that's looking for v. So I don't want this in here. And I've got mass here, but then I've got moment of inertia, and they're kind of incompatible. So what I need to do is I'm going to work on this one to make it compatible with that one, and then go from there. So 1/2 mv squared is what I've got here. But in this case, I'm going to substitute that in for the moment of inertia of a solid cylinder. So I'm not given I for a solid cylinder. You might remember it. I'll look back to my table. Solid cylinder, I equals 1/2 mr squared. So this is going to be 1/2, because there's that, times 1/2 mr squared. And instead of omega, this is where I was jumping the gun earlier. Since v equals omega times r, then omega equals v over r. So instead of omega squared in there, I'm going to put v over r squared. So really, my whole equation is mgh equals all this stuff. So let me write that again. mgh equals 1/2 mv squared plus, now simplifying this, 1/2 times 1/2 is just 1/4. And I've got an m in here. It's all by itself. But then there's r squared on the top, and there's going to be an r squared on the bottom, so the r's cancel, and I get v squared. So this is looking much simpler. So now that I've got this, what would an obvious thing to do be? I just want to simplify this before eventually I'm going to solve for v, but what's a smart thing to do next?
Cross out m.
Yeah, all the m's. I can divide both sides by m, so basically the m's go away. Then what?
Combine their terms.
Yeah, so I've got a 1/2 v squared, and I've got a 1/4 v squared. So this is just basically, let me write gh equals 3/4 v squared. So from there I can multiply both sides by 4 and divide both sides by 3, and that gives me v squared equals 4/3 gh, or v equals the square root of 4gh over 3. So this wouldn't have been nearly so nice or easy. I mean, we'd have to do a lot more math if I had plugged in m in the beginning and plugged in 2 and all that stuff. So this is much easier now. So the answer for the velocity is going to be 4 times 9.8 times the height, which is 2 meters, over 3, and then I take the square root of that. So that's about 40 times 2, 80 divided by 3, and then I take the square root, and it ends up being 5.11 meters per second. So it's a good bit of math, but it's not impossible to do. And it looks like at some point there was a number 3 here, but I felt like it was just extra. So number 4 is asking to do the same thing, but with a hoop. So it's got the same radius, and it's rolling down a ramp from the same height. The only difference is I guess it doesn't say this, but we could assume it has the same mass too. It doesn't matter. Yeah, actually it should have the same mass, I guess. So on this side, does it say if it's a thin hoop? It just says a hoop. Well, oh, by the way, which one do I use? Do I use A or B? They're both, this is a thin hoop, this is a thin hoop. Is it mr squared? Is that the moment of inertia? Or is it 1/2 mr squared plus 1/12 mw squared? A or B? Which one? Jack, Canizaro. Can't hear you, Jack. Can you get closer to your mic?
Wouldn't it be B upright?
Ah, no. I see what you're thinking, but no. Does anybody know why it's A? So it has to do with the axis. They're showing you the relationship between the object and the axis. So if this is the axis, A is rotating around the axis like that. And if this is the axis, B is rotating around the axis like this. So if you have a coin, you put it on the table and you flick it and it spins around, that's the kind of rotation we've got in B. But if you're rolling something down a board, it's going to rotate like an A. So really, when you roll something, the axis is horizontal, but that's the kind of motion we're talking about relative to it. So the moment of inertia is just mr squared instead of 1/2 mr squared. So back to my picture. Now we just got this thin hoop, and everything else is the same. The only difference is this is going to have a different moment of inertia. And if this moment of inertia is mr squared, and the other moment of inertia was 1/2 mr squared, which one do you think is going to be going the fastest at the bottom? This new one with the higher moment of inertia, or the old one with the lower moment of inertia? And maybe I should ask it this way. If rotational kinetic energy is 1/2 I omega squared, if you have a bigger moment of inertia, then when this object gets to the bottom, that means it's going to have, like, this kinetic energy is going to be higher. So basically, the higher the moment of inertia, first of all, the more resistance this is going to have to beginning to rotate, so the slower it's going to move. But also, once it gets to the bottom, the more energy is going to be in rotational kinetic energy. So the less energy is going to be in translational kinetic energy. So the quick answer is higher moment of inertia. It should roll more slowly. We should get a smaller velocity when we get to the end. But it's the same reasoning. So at the top of the hill, this hoop has an amount of potential energy equal to mgh. That's the potential energy. And that's all the energy it has because it's not moving. And when it gets to the bottom of the hill, it's not going to have any potential energy because it doesn't have any height anymore. But it will have translational kinetic energy because it's moving in a straight line down the hill. And it'll also have rotational kinetic energy because it's rotating, because it's spinning around its axis. So this starts out the same way as the previous one. The only thing that's going to be different is I'm going to substitute in a different I there. Instead of it being 1/2 mr squared, it's going to be mr squared. But that doesn't mean we're going to have a simple comparison to this. It'll be a little more complicated. So this is equal to 1/2 mv squared plus 1/2. Now I'm going to substitute in the moment of inertia for a thin hoop, which is mr squared. And I'll do just what I did before with omega. Omega is the same thing as linear velocity over r. So this omega squared becomes v over r squared. So I don't know if I tried to squeeze this in earlier. I guess I'll go down to my next line. This becomes mgh equals 1/2 mv squared plus 1/2 times m. The r squareds cancel. There's going to be an r squared on the bottom of that. V squared. So this is just 1/2 mv squared and 1/2 mv squared. So it's mv squared. Seems like I'm doing something wrong here. It's just so easy. So I get mgh equals mv squared. I can divide them both by m, so the m's cancel out. So it's just v squared equals gh. So v equals the square root of gh in the case of the thin hoop. So the velocity in this case is square root of 9.8 times 2 meters. So that's just about the square root of 20, which is 4.43 meters per second. So it's a little bit slower. And if you wanted something that would roll down the hill and be faster than this, so the hoop is slow, the cylinder is a little bit faster. Looking back at this diagram down here, what's something that would roll down the hill even faster than either of those? In other words, well, I don't want to tell you in other words. I can see one object that'll definitely go faster than the other ones. Some of these are kind of confusing. It's a common object. All right, hint time. It's something with a lower moment of inertia. So moment of inertia of the hoop is a full mr squared, and the moment of inertia of the solid cylinder is 1/2 that. So this goes faster and that goes slower. What's something with an even lower moment of inertia? So the plate is a little confusing. This is sort of comparing apples to oranges because it's not really in terms of R. So maybe, I don't know. It's too, yeah.
Long uniform rod.
Again, possibly, but the one that's in terms of mr squared is the sphere. So this 2/5 is less than 1/2. So this is going to roll faster. These other ones, it gets kind of complicated because they're in terms of L, which is a little different. I don't know. I'd have to really think about those. But the sphere, I believe, is the fastest thing on here, especially in terms of rolling. This isn't going to roll so well. And this one, if you look at its axis being like that, it's not going to roll very well either, and neither is this. That's sort of tumbling end over end. That's what that's doing. All right. So the next question, I don't even know if it's necessary, but I sort of feel like it's on the sheet, so for good measure, I'll finish it up. This just says to compare the speeds of thin hoops and solid cylinders in general after rolling down ramps. So basically, the velocity of a solid cylinder is going to be 4gh over 3, and the velocity of a thin hoop after rolling down a ramp is going to be square root of gh. So if we wanted to find the ratio of those, you could just divide them. V cylinder over V thin hoop would just be the square root of this over the square root of that, square root of both things. GH over 3 divided by GH. So these cancel out. And it's just the square root of 4/3. So 4/3 is a little bit more than 1, and you take the square root of that and you get a number closer to 1, but still over 1. So the velocity of a cylinder when it gets to the bottom of the hill is a little bit faster than the velocity of a thin hoop, which we didn't really need to do this to know it because we showed it there. So the assignment is really just more practice like that. There are 5 questions here. This one is about a hoop rolling down a hill. How fast is it going to go? This is a solid disc rolling down a hill. This is, here we get the kinetic energy of the Earth on its axis. That's a little different. Rotational kinetic energy of the Earth in its orbit about the sun, which means here's the sun, here's the axis of rotation, here's the Earth going around the sun like that. That's a different kind of a case. This is the Earth rotating around like this. And then finally, a ball with an initial velocity rolls up a hill. How high is it going to go? So that's it. Work on those. The answers are all right here. If you need help, I'll